Bismillahirrahmanirrahim. Assalamualaikum. And good morning, everybody. Or you can hear me?
Yes, sir.
Okay.
Yes, sir.
Can you see the slides?
Yes.
Okay.
Yes,
Good.
sir.
Okay. So today is basically that we are going to continue with the OpAmp circuit application. Altogether, basically that we have two, four, six, 7 applications. Okay, and hopefully that we can cover all the applications today. Okay,
Okay, sir.
so it'll be about more than about 32 slides altogether for today. So you ready to start? Any question from the lecture last week? Any question? All clear. What about the assignment that I gave you? Three assignments. Those easy or not easy? Eh?
Not easy, sir.
Not easy. Yeah. So maybe on Thursday, we will. You can ask me questions about the application, because on Thursday I'm going to what I'm going to do is that I'm going to do the examples and exercises for the OpAmp circuit application. Today I'm not going to go through the examples. I'm just going to go through the theory of it. Okay.
Okay, sir.
Okay.
Okay, sir.
Before we go into the specific application, we look at we talk about the feedback previously that I mentioned about feedback. So we are going to see why we need feedback when we do the OpAmp circuit application. Okay. So first of all, what is a negative feedback? The negative feedback is basically that the loop, where the output signal basically is feedback to the negative terminal of the negative input of the amplifier. So the inverting input effectively makes the feedback signal 180 degrees out of phase with the input signal. So that is actually the negative feedback. So this is actually the part of the negative feedback. And negative feedback, you have a certain circuitry. Maybe you have the resistance circuits and or even RC circuits, that kind of thing. So in this lecture, we use a lot of the negative feedback in our application. So when you say about negative feedback, so basically this is it. This is the examples of the circuit, the configuration for the negative feedback, where you have part of the output is feedback sent back to the negative terminal of the OpAmp. Okay, the input terminal of the OpAmp. So it's called a negative feedback. Okay. Any question on negative feedback? No question. So I go further. Why do we use negative feedback? You remember that the typical value of amplifier open loop gain, so AV or AOL, the open loop gain is actually very high. It's about in the order of 100,000, 1 million, that kind of thing. Remember? So therefore, an extremely small input voltage will drive the output into, will drive the op-amp into its saturated output state. For example, let's say you have about 1 millivolt. So 1 millivolt of input will produce 1 millivolt multiplied by 100,000 will give you 100 volts, right? Right? 1 millivolt is actually one thousandth of a volt, right? So 1 millivolt. So multiply by 100,000 will give you 100 volts. So it's very high. So it's actually not suitable for linear application because the op-amp went into a saturated output state. So therefore, we need to use that negative feedback to limit the gain of the amplifier so that the amplifier will operate in the linear region, right? So if you look at the comparison of the characteristic of an op-amp without negative feedback and compare with the characteristic when you have a negative feedback. So in terms of these 4 parameters, the voltage gain, you look at the open loop gain is too high for linear amplifier application if you don't have the negative feedback. So when you put in the negative feedback, therefore the closed loop gain is set to desired value by the feedback circuit. Basically that you as a designer, you will be able to set, to decide what is the suitable or the desired gain that you need by playing around with the feedback circuits, by changing the resistance value of the feedback circuit. Okay, so this is in terms of the voltage gain. When we go to when we do the comparison of the input impedance, okay, without the negative feedback, the input impedance is relatively high. But when we can you mute your mic? Whose mic is that? Okay. When you compare the input impedance, Z or Z is actually the impedance. Impedance is the real part of impedance is the resistance. Okay. So basically Z is equal to R plus X or J, the imaginary number, the complex number. Z is equal to R plus J X. Okay. So the input impedance for the negative feedback is relatively high. So you see, you can go to table 12-1 in the textbook, in Floyd textbook, to see what kind of numbers that they have for the impedance. Okay, and when we compare with the amplifier with negative feedback, this actually you can increase or reduce the value of the impedance depending on the type of circuits that you want. Right? So you can control the input impedance. Right? The same thing with the output impedance. Output impedance is basically relatively low when you don't have the negative feedback. But when you have negative feedback, you can control, you can reduce to a desired value, right? You can change the output impedance, right? And the 4th parameter, which is the bandwidth, without the negative feedback, relatively narrow bandwidth because the gain is so high. So you have narrow bandwidth. When you have the negative feedback, you reduce the gain. Therefore, the bandwidth is you expand the bandwidth, so it's significantly wider compared to the negative when you don't have the negative feedback. Okay. Who knows? Maybe this will be in the test. Right? Any questions so far? So that is the the usage of the negative feedback in our OpAmp circuits. Because we want to control the voltage gain. You can set the voltage gain. You can change the input impedance, increase or reduce. You can change the output impedance and also the bandwidth, that you need a bigger bandwidth in your application for the in the linear region of the application. Okay. So now we are going into the first OpAmp circuit application, which is the inverting amplifier. Inverting amplifier, from its name, you know that the output is basically that is the inverse of the input. So that's why it is inverting. So the input is basically that at the negative terminal of the OpAmp. Amplifier basically that is amplifies the input. So it makes larger the input larger at the output. Okay, so the circuits that we have is something like this. Okay, so you have the input signal at the negative terminal of the OpAmp, and the positive terminal is grounded, and you have the output feedback to the input, back to the input. So you have this circuit. So if you see this type of circuits, you need to recognize that this is actually an inverting amplifier. How to recognize? You have the input at the negative terminal, and positive terminal is grounded, and you have the negative feedback to the negative terminal. So this is actually most widely used constant gain amplifier because of its simplicity and better frequency stability. It's simple. You only need amplifier. You need two resistors and a power supply to bias the circuit and the input, the input source to the circuit. That's it. 1, 2, 3 input generator and the biasing. So 1, 2, 3, 4, 5. So about 5 components, right? So the input signal to be amplified is connected to the inverting terminal. This is the minus terminal, while the non-inverting terminal is grounded. The configuration uses negative feedback to stabilize the voltage gain. So to control the gain of this inverting amplifier, basically that you control the value of RF and R1. We see later, right? So negative feedback occurs when a portion of the output voltage is connected back to the inverting input such that it subtracts from the input voltage, thus reducing the voltage gain but increasing the stability and bandwidth of the amplifier. So that is actually the role of negative feedback. So this signal, the output signal, feedback to the negative terminal and subtract from this input signal. The input signal is subtract the input signal. So by doing that, it's actually reduce the voltage gain. So basically that the closed loop gain will be reduced, will be lower than the open loop gain of the amplifier. And this will increase the stability and also will increase the bandwidth. Right? So, what is the golden rule of this inverting amplifier? If there is negative feedback and if the output is not saturated, it is true that this statement will be true. This condition will be true. Both inputs are at the same voltage. So when you have this negative feedback, okay, when you have the negative feedback, so both input, basically V minus and V plus are the same, almost the same. This almost the same. The voltage at the minus terminal and the positive terminal is almost the same. That is the first condition, the first rule. The second rule is that there is no current flow in or out of the input here, this. The current through this terminal, this input here. Okay? Not this part, but this one. This part, this. This part. So this I minus is equal to 0. Basically that this will lead to the virtual short circuit between the two inputs, and the inverting terminal is at the virtual ground. So basically that when V minus and V plus is almost equal, and there is no current flowing through this, therefore, this actually creates a ground. So create a ground at here, at this node. And this is actually a virtual short circuit between V minus and V plus. This will create a virtual short circuit. Therefore, this becomes a virtual ground. Okay? Because V1, V plus is connected to the ground, right? And if this is short circuit virtually, then this become virtual ground, because this also will follow the voltage of this terminal. So that's what we call a virtual ground. Okay? Any question? So this is the concept of virtual ground. As what I explained just now, since the difference between the input signal, the difference between V plus and V minus is 0, then the signal voltages at the two input must be the same. Yeah. So if this is 0, this is 0, therefore these two inputs is the same. It must always be the same. Since the non-inverting is held at the ground, 0 volt, a virtual ground exists at the inverting input. Okay? So V plus is equal to V minus equal to 0. Thus, the inverting configuration, we can assume that the inverting input is virtually connected to the ground. So the point P, this node P, is known as virtual ground. So when we talk about virtual ground in the inverting amplifier, we talk about this point to be 0 volt. Okay?
Tak faham, sir.
Tak faham? The ground is 0 volt, right? Right?
Yes, sir.
So virtual ground, then it's 0 volt here. Why is virtual ground? Because you have a virtual short circuit here. Because V1, V plus and V minus is equal and is equal to 0, because V plus is connected to the ground. Okay? V minus and V plus is equal. Here, this ground rule. Okay? You follow the two ground rule, therefore, you have the virtual ground. Here. V plus and V minus is equal, and the current here is 0. There is no current flowing here, therefore, and it's actually virtual short circuit. So this is virtual ground.
Oh,
Okay?
faham, sir, faham.
Okay. So now we are going to analyze the uh, inverting amplifier. So now we have these circuits and we know this is the ground. So using the KCL of this point, what is KCL? The Kirchhoff current law. What does it say? This the summation of the
Summation
current
of current is 0.
and entering a node is equal to the summation of the current leaving the node, right? So
Equal.
in this case, you have three currents. You have IR1 going into the node, and you have the feedback current, which is IRF, going into the node, and you have I minus leaving the node, right? So this sum should be equal to 0. So IR1 plus IR2 is equal to I minus. And from the golden rule just now, I minus is equal to 0. So this is actually equal to 0. Therefore, it gives you IRF is equal to minus IR1. So IRF is equal to IR1 because I minus equal to 0. Right? Clear? So IRF, which flows back to the inverting terminal from the output, is appropriately termed as feedback current. So this IRF is basically a feedback current because it represents an input to the amplifier that is fed back from the output. This is from and not from. So by using the Ohm's law, V equal to IR, so I is equal to V over R, right? So therefore, VRF is here, divided by, therefore IRF is equal to the voltage across this RF divided by the resistance RF. So you get this, and minus IR1 is this one, is minus IR1 is the voltage, VR1, voltage across this R1 resistor divided by the R1, the resistor. So you have this. Okay. What is VRF? What is the voltage across here? This is actually equal to V out minus V1. Okay, divided by RF. And what is the VR1? VR1 is basically that V1 minus V minus divided by R1. So you get these equations. Okay? Clear so far?
Clear, sir.
Clear? Huh? Clear?
Tak nampak lagi.
Clear.
Yes, sir.
Siapa yang tak nampak?
Benda ni guna law je kan, sir? Macam biasa.
Yes, Ohm's law. Just V equal to IR. Now we have this equation. V out minus V minus divided by RF is equal to minus V1 minus V input actually. V input minus V minus divided by R1. And we know that, okay, from this diagram, we know that V minus is this equal to V plus, right? Because this is actually virtual short circuit. Virtual short circuit between these two terminals, plus and minus. Therefore, V minus is equal to V plus. And what is V plus? V plus is 0 volt because it's connected to the ground. So we substitute the V minus with 0. So you get V out divided by RF equal to minus V1 V in over R1. So this, because you have a virtual ground, V plus equal to V minus equal to 0. Therefore, you have V out divided by RF equal to minus VI divided by R1. And rearrange, you get V out is equal to minus RF over R1 VI. Okay, and what is the gain? The gain is basically that the output voltage divided by the input voltage. So the gain of the amplifier AV is equal to V out divided by V in is equal to minus RF over R1. So this is actually the gain, the closed loop gain of the amplifier. So you see now that we can control the closed loop gain of this amplifier by playing around with these two resistors, RF and R1. So previously, the input gain, AOL, that you cannot control because it's actually decided by the manufacturer when they design the OpAmp. But now, you can use this OpAmp, you can control the gain by controlling the closed loop gain. So AV. So AV for the closed loop amplifier is minus RF over R1. So that is the formula for the inverting amplifier. Any question on the theory of inverting amplifier?
So kita boleh kawal dia guna dia punya input lah sir.
Basically, the input can be anything, but you control the gain because this the application is to amplify the signal. The signal can be sine wave, cosine wave, can be step function, can be a ramp, can be sawtooth, anything. But you control the gain so that the output is actually the output is equal to the gain multiplied by the input. Okay.
Oh.
And what kind of gain that you want is basically depending on this configuration, RF over R1. Let's say you want this amplifier to multiply, to increase the input signal by 10. So you select RF is equal to 10 kilo ohm and R1 is equal to 1 kilo ohm. So you get minus 10. So your signal, your input signal is amplified by 10, but in a inverse, out of phase by 180 degrees. So that's why you have a minus sign. So if the input is positive, the output, it becomes negative, but with a larger amplitude. Okay, clear? Clear so far?
Ya, yang tadi yang saya kata kalau nak tinggikan dia punya input, naikkan RF ke turunkan?
You play around with this. This is the gain. RF over R1 for the inverting amplifier.
Okay, faham. Saya
Okay.
dapat. Okay, sir.
Anybody who has other questions?
No, sir.
Clear? Okay. Okay. Now we are done with the inverting amplifier. Kejap Berapa dah? Setengah jam. Next. If you have inverting amplifier, then you have non-inverting amplifier because you have non-inverting inputs. So, non-inverting amplifier, therefore you ground the negative terminal and the input to the amplifier is from the positive terminal, just like shown in the diagram. And still, you have the negative feedback circuit. This is still the negative feedback. It doesn't change. The only thing changes there is that the input of non-inverting, of inverting, you ground, and the non-inverting input, you put a signal input that you want. Okay, compare with the spirit. Okay, you look at this. Compare with this. Same components. The only changes is that this one is ground, this one is connected to the V in, VI. Okay. So you ground this one and this one VI. So this is a non-inverting amplifier. So don't get confused. How to recognize whether it's inverting amplifier or non-inverting amplifier? You look at where the input is, where the VI is. If VI is at the positive terminal and negative terminal is ground, therefore it's a non-inverting. So the output here will be in phase with the input. If input is positive, the output is also positive. The only difference is that the amplitude will be changed by the gain of the amplifier. So now, what is the gain of non-inverting amplifier? We will see later. For the inverting amplifier, you know, AV is equal to minus RF over R1. But now we have changed the configuration with the input configuration. Therefore, the calculation for the gain, the formula for the gain of non-inverting amplifier must be different than the inverting amplifier. So now we do the analysis to find what is the formula for the non-inverting amplifier. Still, using the concept of virtual circuit, virtual short circuit. Okay. This still holds that you have the positive terminal and negative terminal of the op-amp is in the virtual short circuit. If this is a virtual short circuit, therefore V plus and V minus has the same voltage. What is the voltage? What is the voltage? It's actually
V1.
equal to V input.
V1.
V input, VI, V input. So if V plus is V input, VI, therefore V minus is VI. It's the same. So now, this is VI, this VI here. Okay? Now, what is the KCL of this terminal? Basically, you have this current, and this current is still 0, right? So it's the same formula. It's the same. You start with the KCL. Still the same.
IRF
IRF.
plus equals to
IRF minus IR1 minus I minus equal to 0.
Yes.
So it's IRF is equal to IR1 plus I minus. So, but I minus is equal to 0 because this is actually virtual short circuit.
yes.
So I minus equal to 0. Therefore, IRF is equal to IR1. So now again we use the Ohm's law. What is IRF? IRF is basically VRF divided by RF. Here. What is IR1? IR1 VR1 divided by R1. And what is VRF? VRF is actually that V out minus. This is actually minus VR1 here. This point is VR1, right? Because this point minus 0 is the same as VR1. So VR1 is here. So V out minus VR1 divided by RF. And here, what is the VR1? What is
VR1
the IR1? IR1 is VR1
oh,
minus 0 divided by R1. So you get this. Therefore, V minus is actually equal to VR1. And virtual short circuit, V1, V plus equal to V minus equal to VI. Okay. So VR1 is equal to, what is VR1? VR1 is equal to VI. So VI is here. So you substitute VR1 is equal to VI. So you get V out minus VI divided by RF is equal to VI divided by R1. Rearrange the equation. So you get V out is equal to V1 plus V1 RF over R1. So V out is equal to 1 plus RF over R1 not multiplied by VI. Okay. Clear? Clear. So what is the gain? The gain is actually V out over V in. So V out over V in. So you have 1 plus RF over R1. So this is actually the non-inverting amplifier closed loop gain. See the difference between the non-inverting and the inverting? Non-inverting is basically 1 plus RF over R1. That is the gain. For the inverting, is minus RF over R1. Okay? So that is the
okay. Okay.
the gain for the non-inverting amplifier. So let's say you have a signal that you want to amplify by 100. So V out, let's say you have a 1 volt and you want, let's say you have 0.1 volt and you want to amplify it to become 10 volt. So what is the gain? 10 divided by 0.1 is equal to 100, right? So it's AV is equal to 100. If AV equal to 100, therefore RF over R1 is equal to RF over R1 is equal to what? If AV equal to 100.
99.
Equal to 99, right?
Yeah.
So what is the combination of RF over R1 to give you 99? Give you 99.
99 over 1.
So RF is equal to 99 kilo ohms divided by R1 is 1 kilo ohms.
1 kilo. Okay.
So that is the value of RF and R1 to give you the gain of 100.
100.
Yes. So that is actually how you design the circuit or how you analyze the circuit. Normally, the analysis, normally we give you the value RF and R1 and ask you to calculate. Okay. But if it's the design problem that you are given the gain, you go backward. Basically that you are given the gain and you select the RF and R1 to give that gain. Okay.
InsyaAllah.
Tak faham? Faham tak?
Faham.
Okay.
Faham.
Saya takut nanti soalan putar belik, lepas tu tak faham dah. Tapi yang ni faham.
Betul je. Takut V1 tu buat lain dah tak risau dah. V1 jadi VA ke, VB ke.
Biasa je. It doesn't matter what it is called. As long as you understand there is an input. There is an output, there is an input. So what is the gain? The gain is the ratio of the output over the input. And you look at whether it's inverting or non-inverting. If it's inverting, therefore the gain is minus RF over R1. If it's in non-inverting amplifier, is 1 plus RF over R1. Simple. Okay. This is another application. It's unity follower or voltage follower. So basically that the gain is equal to 1. Whatever that's whatever the input, that value is actually appear in the output. So the gain is equal to 1. So this is the circuit. The unity follower is a special case of non-inverting amplifier. This is what we also call a voltage buffer or a voltage follower. Right? So unity follower is a special case of non-inverting amplifier where all of the output voltage is fed back to the inverting input by a straight connection. There is no resistance. It provides a gain of unity with no polarity or phase reversal. For the equivalent circuit, it is clear that V out is equal to V1. And that the output is the same polarity and magnitude as the input. So if you are given circuits, connections of different amplifier, you should recognize this configuration, what is the gain? This configuration, how to calculate the gain and all those kind of things. Right? So this is called a unity follower or voltage follower. Any question on this?
No, sir.
No. Okay, I can
No, sir.
continue.
Take 5, sir.
Take 5.
Saya tengok
Sir.
Take 5, sir.
Kan?
Okay. Right now is 11:17. So hopefully that I can finish by 12 something.
Alright,
Okay.
sir.
Alright.
saya nak cover semua application ke, sir?
Yes. I want to cover the application so that we can do exercise on Thursday.
Okay, sir.
Okay, so that you understand the concept, the theory first. Okay.
Okay, sir.
So 11:20 something we start again. We'll continue with summing amplifier after this. Just look at the circuits and try to understand. Summing amplifier is also called as an adder or a summer. Okay, semua dah ada?
Dah sir, dah.
Dah. Dah boleh start?
Boleh sir.
Semua ada? Can I start?
Boleh sir.
Boleh. Okay.
Boleh sir.
The next one, this is the third amplifier, third application, which is the summing amplifier. As the name indicates, basically that the summing amplifier is an adder. It's actually to add the input signals and present that addition at the output. So this useful OpAmp circuit is based on the inverting amplifier. So the output is actually with a minus sign. So the amplitude of the output is the addition of the input signals, of the total of the input signal, but the sign is reverse. So if you want to have the same sign, so you need to invert that using the inverting amplifier with a gain of 1. Right? So this circuit is used to add signal sources. It has 2 or more inputs. So in this example, you have 3 inputs. So it's 2 or more. It can be many. And its input voltage is proportional to the negative of the algebraic sum of its input voltages. Okay. The primary advantage of using OpAmp as a summer is that the summation occurs independently of load and source impedances, so that sources with different internal impedance will not interact with one another. So basically that the internal impedance of this input V1, V2, V3 will not affect the output. Will not affect the and it will not interact with each other. Right? So you can ignore the internal impedance of the input and also the internal impedance of the output. Okay. So your calculation is only based on the value of V1, V2, V3 and R1, R2, R3 and RF to get the output here. So now we do an analysis of this to look at what is the formula for summing amplifier. So we look at this input and we know that from the golden rule that V1, V plus and V minus are equal to 0. Why? Because V plus is connected to the ground.
To the ground.
Yes. So basically at this point, it's actually 0 volt. And the I1 is equal to 0. Here, this is from the golden rule. You always remember that basically V plus equal to V minus, and another rule is that the I minus is equal to 0.
0.
The I input is equal to 0. This current is always 0. Right? So if the current is, so this is actually a node, right? This one node. So you can use the TCL. So IR1 plus IR2 plus IR3 minus IRF equal to 0. So this IR1 plus IR2 plus IR3 plus IRF is equal to I in, and I in is equal to 0. So therefore, IR1 plus IR2 plus IR3 plus IRF is equal to 0. What is IR1? IR1 is actually V1 minus V minus divided by R1. IR2 is V2 minus V minus divided by R2 plus IR3 is V3 minus V minus divided by R3 plus IRF is basically a V out minus V minus divided by RF equal to 0. What is V minus? V minus is actually equal to 0 because V minus is equal to V plus and V plus is grounded. So therefore it's equal to 0. So you substitute V1 minus 0 divided by R1 plus V2 minus 0 divided by R2 plus V3 minus 0 divided by R3 plus V out minus 0 divided by RF. So you get V1 over R1 plus V2 over R2 plus V3 over R3 plus V out over RF. Rearrange the equation. So therefore, the summer, the output is that V out is equal to minus RF times V1 over R1 plus V2 over R2 plus V3 over R3. So this is actually the equation of the summing amplifier. The input, the output is basically that equal to the summation of the proportion of the input signal. You see this? Actually, what is the proportion? The proportion is according to the gain. What is the gain? For example, if this signal, this V1, the gain for V1 is really RF over R1. What is V2? What is the gain for this signal? It's RF over R2. What is the gain for this signal? It's RF over R3. So this is actually the proportion. If you want a summing amplifier of V out is equal to V1 plus V2 plus V3, therefore you make the value of RF over R1 equal to 1, RF over R2 is equal to 1, RF over R3 is equal to 1. So maybe this is 10 kilo, this is 10 kilo, 10 kilo, 10 kilo. So it's 10 kilo ohm divided by 10 kilo ohm is 1. So you get V out equal to minus V1 minus V2 minus V3. Clear? Understand?
Value akan diberi.
It depends on the question. Whether I give the value of RF, R1, R2, R3 and ask you to calculate what is the output. Or I say that, okay, I have V1, V2, V3 and this is the output and I want the output to be this. Design what is the value of RF, R1, R2, R3. For last semester, this summing amplifier, actually the question for the test 1, I think. So there are some parts that you need to design. First, I give you the value, you do the calculation. Then after that, I'll say, why not? Why if we change the value of R3, for example? So what is the output now? Then after that is it. Okay, if I want to make this into a summer with certain value, the gain of certain value designed for me, the secretary. I do that also. So it's a lot of things that can be done with the amplifier. A lot of questions that can be designed for the test. Okay. So this is actually the summing amplifier. Any question? So now it's a bit more difficult, but the concept of inverting amplifier still applies. If you look at this, actually, this is really a inverting amplifier for V1. And since you have 3, then you add the output of 3 amplifier actually. The different gain is depending on the RF, R1, R2, R3. Even though you use one amplifier, but actually it can have a different gain. This one gain. This one is one gain. This one is one gain. So you see that, okay, the gain of each signal is not affected by the other signal. For example, for the R1, for the V1, it's not affected by the V2 or V3. It's not affected by this R2 and R3. Okay? This is the gain for V1. This is the gain for V2. This is the gain for V3. Right? Clear? Clear?
Boleh sir?
No. I want to continue. Okay? Boleh?
Yang lain macam mana?
Faham
Ada
tak?
news? Faham ke?
Faham sir.
Okay. Examples of the summing amplifier. Now, since it's a bit more difficult, so I give the example. Okay. Determine the output voltage for the summing amplifier in the figure below. So you have two inputs, V in 1 and V in 2. You are given of the value of 0.2 volts. V in 1 is 0.2 volt, V in 2 is 0.5 volt, and the circuit is that R1 is 1 kilo ohm, R2 is 1 kilo ohm, and RF is 10 kilo ohm. Find the output. So find the output. So from the previous slides, you know that the output is equal to minus RF times V in 1 over R1 plus V in 2 over R2. So this is actually the formula for the output. So you substitute the value. What is RF? Is 10 kilo ohms. What is the V in 1? Is 0.2 volt. What is R1? Is 1 kilo ohms. What is the V in 2? Is 0.5 volt. What is the R2? Is 1 kilo ohms. So you substitute the value and you calculate. So the output is actually minus 7 volts. Looks simple, right? If you understand, memang it's simple. Any question on this example? Any question? Do you have question? No question?
Oh sir.
Okay, now I can continue. Now it's a difference amplifier. Just now is the summing amplifier. Now it's a difference amplifier.
Difference.
Difference.
Application yang keberapa sir?
Application.
Yang ni application.
You have basically the inverting, non-inverting. Then after that you have summing. Then now you have a difference amplifier. So basically that you do the inverting is basically you inverse the sign. Non-inverting basically just amplify. The summing is you add. Difference is you subtract.
Alright.
Okay, difference is you subtract. This is not integration or differentiation. This is only difference amplifier. So difference amplifier now is a combination of inverting and non-inverting. Why is an combination? Because if you have this input here, this input is a inverting amplifier, and this input here is a non-inverting amplifier. Okay. So now you have previously, if it's non-inverting, this is ground. right?
Okay.
You don't have this. This is ground. This part is ground. For inverting. For non-inverting, you ground this part. But this is the signal. But now difference, actually both are connected to the input, different input signal, V1 and V2. V1 and V2. So the circuit frequently used in situation where the difference between two signals needed to be amplified. So what you want to amplify is that the difference of these two signals. So now we want to do the analysis to find what is the formula for the V out. Okay, the difference. V out is basically the difference. You amplify the difference of V1 and V2. Of course, it's depending on the difference is depending on the ratio of R1, R2, R3, and R4. Okay, now the circuit analysis. How are we going to analyze this? Let's say R1 is equal to R3, R1 is equal to R3, and R2 is equal to R4. So basically that the ratio of this and the ratio of these are the same. True. This is our assumption. R1 equal to R3 and R2 equal to R4. So from the Kirchhoff current law, so you have IR3 plus IR4 is equal to I equal to 0. So you have this equation. And another one is that IR1 and IR2 equal to 0. So you get this. So basically IR1 is equal to IR2 plus II equal to 0. So since, yes, clear?
Tadi kata tadi IR1
This
plus
IR1, IR2. Yeah, KCL. Kirchhoff current law.
Oh, okay sir.
Okay. So since II is equal to 0, therefore you can rewrite the equation like this: IR3 plus IR4 equal to 0, and IR1 is equal to IR2. This, and therefore IR3 equal to minus IR4. So you have two equations here. IR3 is equal to minus IR4, and IR1 is equal to IR2. What's coming in is equal to what going out. Right? So from equation 2, this IR1 equal to IR2, then we can write this. What is IR1? IR1 is basically VI or V1 minus V plus divided by R1. What is IR2? IR2 is V plus divided by
plus
R2. So you get this. So rearrange the equation. So you get V1 R2 minus V plus R2 minus V plus R1 equal to 0. So what is V plus? Rearrange this equation. What is V plus? So basically you rearrange, you take out this V plus R1 is equal to V1 R1 minus V plus or this. So you get this. So basically that V plus is actually the voltage divider of V1. Basically V plus is equal to R2 over R1 plus R2 times V1. So this is the voltage for V plus. This is the voltage for V plus. Now, continue further. Now we look at this part. Now we want to find the V minus. Okay. From equation 1, IR3 is equal to minus IR4. This IR3 is equal to minus IR4. So, what is IR3? IR3 is basically V2 minus V minus divided by R3. What is IR4? IR4 is V out minus V minus divided by R4. So rearrange, you get R4 V2 minus V minus equal to minus R3 V out minus V minus. Rearrange the equation, so you get V minus equal to R2 over R1 plus R2 V1. Actually V2.
Voltage
V2.
drop.
V2, right? This is actually, this part is actually from the previous one here. R2 divided by R1 plus R2. This is actually, this equation is from here. And you know that V plus and V minus is the same point, because this is virtual ground. Remember? This is virtual ground. It's always V plus equal to V minus. So this R2 over R1 plus R2 V1 is from the previous equation, from previous slide, from here.
Yes.
So now V minus, you substitute with this value, this V minus here. Okay? V minus in this equation, you substitute with this value. So you get this. V out R3 equal to minus V2 R4 plus, this is actually V minus times R3 plus R4. Since R1 equal to R3, we assume this R1 equal to R3 and R2 equal to R4. Therefore, you reduce the equation to this. V out R1 equal to minus V2 R2 plus R2 over R1 plus R2, V1 R1 plus R2. So you get this. Therefore, V out is actually equal to R2 over R1 times V1 minus V2. You see, this is actually the difference.
All right, sir.
V1 minus, and this is the gain. Okay.
Sir, saya nak tanya.
Yes.
Apa ni yang kat sini dikata since R1 equals to R3 and R2 equals to R4. Ada ke kemungkinan R2 dengan R4 tu lain?
Ada.
Oh, so
Kalau saya nak buat susah soalan.
alright. So gain dia akan jadi lain lah, sir.
Yes.
Alright.
It's possible because it can be any value. R1 can be any value, R3 can be any value. It doesn't have to be the same. So if it's not the same, therefore the ratio will be different. Basically that the ratio will be
Whether bigger or
yes.
smaller.
Yes. Right? So if I want to make it easier for you, I will give you the same value lah. R1 equal to R3 and R2 equal to R4.
Easy lah, sir.
Nanti example, nanti I will show both. I show both. Right? Okay. Now,
Yes, sir.
Okay.
the next one we'll go to integrator. So basically that we almost done actually. Integrator and differentiator after this. Apa tu? Okay, integrator. Basically that an integrator is, remember your calculus that you want to integrate the function. So this integrator is that something which is that you need something which is non-linear. So which component that give you, remember that from the last semester that they get di dt or dv dt, that we give you that kind of functions. So basically that is a capacitor or inductor, right? Remember? dv dt dc di dt.
Tak ingat sir.
Tak ingat? Kena ingat lah. So the integrator is actually a circuit with the capacitor in it. An OpAmp integrator simulates mathematical integration, which is basically a summing process that determines the total area under the curve of a function. So the circuit is as given here. So instead of a resistor here, now you have the capacitor. Because IC is equal to dVc dt, right? Right?
Okay, yes sir.
Yeah.
Right, sir.
So
Betul lah sir. Betul.
So you have these circuits. Okay. So for the integrator, you get still the golden rules follows. Okay. That
Okay. Yes.
virtual short circuit here. So the V plus is actually equal to V minus, which is equal to
And
0 volt. Right?
I
So
equals 0.
I in equal to IC
0.
plus II. So this is actually II is equal to 0. So I in is equal to IC. Right? So I in is constant. So is IC. So if I in is constant, IC is also constant. Right?
Sir, IC punya arah memang kat situ sir.
Because this we use the plus sign here.
Oh, okay.
Okay. Right?
Plus
The
sign.
resistor dia pergi ikut sini. Right? Okay. So this is for capacitor. Can you have a plus sign and minus sign? Then you have the polarity. Remember? So the capacitor, you have that. So now, the circuit analysis. Let's say you have a step function. So V out is actually will be a ramp. So V out is the same as the voltage on the negative side of the capacitor. The rate at which the capacitor charges is set by the ratio of IC over C. Since IC is equal to V in over R in, therefore, the changes of the output divided by the change of the time is equal to minus V in over RI C. This is the formula. This is actually the integration. dV dt. dV dt is equal to V in over RI C. So this is actually the integration.
I see.
So this is a practical integrator is actually you have an RF, not just the capacitor. This is the practical integrator circuits. Okay. Now is the last one, is in the differentiator. The differentiator is actually simulates the mathematical differentiation, which is the process of determining the instantaneous rate of change of a function. So this is the circuit analysis. For differentiator, KCL is V out is equal to IR RF equal to IC RF. So V out is equal to minus VC over T RF C. So if you have a triangle input, so the output will be this signal square. No. Okay. This is a practical integrator. That you have the resistor are in there. So this one is basically that you just aware of integrator and differentiator. I don't know whether it will be in the test or not. So most probably not. Okay. So I will obviously just concentrate on the inverting, non-inverting, summing, and difference amplifier, differentiator and integrator. Yes, you just know, you just aware there is, and if the question comes, maybe you just recognize how does it look like. That's all.
All right, sir. Thank you, sir.
So now, this is an example. This something will come out in the test, something like this. Now, an example. Let's say I have a circuit shown as in the diagram there. First, maybe I say that identify what is OP1 and OP2. So can you identify what kind of amplifier is that? What is OP1?
Unity.
Unity. Unity. Okay. That is correct. What is OP2?
Inverting.
Inverting amplifier. Okay, that's correct. So determine the V out one. What is V out one?
V out one.
Yes.
V out one.
Unity amplifier.
Oh, is it 1.5?
1.
Is it 1.5 or is it minus 1.5?
Minus saja.
I'm asking you, is it 1.5 or minus 1.5?
Positif sir. Sama. V1 equal to V out.
Macam positif.
Macam positif.
Yes, it's positive because from the positive terminal. Remember the unity
Jimmy
amplifier. Unity amplifier is actually a special case for non-inverting amplifier. So V out one is actually 1.5 volt plus 1.5 volt.
Sebab dia from plus.
Yes, it's from this terminal. Remember, this is really a special case of non-inverting amplifier. So V out is equal to 1.5 volt. So you have 1.5 volt here. So what is V out? This is actually, you say that is a inverting amplifier. What is the gain of inverting amplifier? Equal to the AV is equal to minus RF over R1 multiply by the V in, right? Because this now VO1 is the input to this amplifier. So now basically what is the gain is 100K divided by 22K. So
K times 1.5.
So 100 divided by 20 is 5, right?
Yes.
So basically 1.5 multiplied by 5. So
11.5.
11.5. But this is a inverting. So it's minus 11.
Minus 7.5.
Okay, minus 7.5.
Yes.
So this is the first one. It's a voltage follower or unity amplifier. So V out is equal to VE. Thus, V out one is 1.5 volt. Correct. The second one, this OP2 is the inverting amplifier. So the formula for the output is equal to minus RF over R1 times VUI. Therefore, you get minus 7.5 vote.
Oh,
Okay, you are done. Example number 2. Name the function of each OpAmp. What is OP1?
unity.
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 Unity amplifier. What is OP2?
OP2
Inverter.
inverting.
Inverting. What is OP3?
Non-inverting.
Not
Non-inverting.
inverting. Now, find the V2 and V3.
Macam biasa. Cari OP1 tu.
OP1.
So,
VO.
first,
One.
okay. What is VO1? Because you want to find the input to these two amplifier, right?
2 volt.
Yes.
So, positive 0.2 volts. Okay, here. So the input to both amplifier is 0.2 volt. So what is the output for OP2, which is V2? What is the value?
over 20k.
And
So
100k over
20k divided by 20k is actually 10, right?
10.
10.
So
Yes, sir.
0.2 multiplied by 10 is 2 volt.
2
But
volt.
this is inverting, therefore it's minus 2
2
volt.
volt.
Minus 2 volt.
Okay, what about this one?
Formula.
What is the gain for this?
K over 10k.
V naught 1 plus RF over R1.
So 1 plus 200k divided by 10k. So
10K.
200k divided by 10k is
20.
20. 20 plus 1 is 21.
21.
So what is V3? V3 is
21.
0.2 multiplied by 21.
21.
So what is the value?
4.2, sir.
4.2.
4.2, sir.
Okay. So this is the first one, okay? Voltage follower is 0.2, correct? OP2, inverting amplifier, the V2 is minus 2 volt, is correct? The third one is the OP3 is non-inverting amplifier, and this is the gain. So 1 plus 200 divided by 10 is 100, so 4.2 volt. Correct.
Okay, sir.
So now for your exercise, can you do that?
Yes, sir.
Okay.
VO. Okay. Wow.
Boleh buat.
Kita cuba, sir.
Guided, sir.
Guided.
Is
Sama-sama.
Okay.
InsyaAllah.
Now, I want you to do these 3 exercises and submit on Thursday.
Allah.
Okay, sir.
Okay. Exercise 1,
guys.
exercise
Saya
2, and exercise 3.
Sir, nak jawapan je boleh, sir?
Timba dia Google.
Nak
Jawapan,
je, sir?
jawapan.
Hah?
Jawapan dia.
Nak jawapan je.
Mana boleh bagi jawapan ni quiz. Nanti.
Sir.
Oh, quiz eh?
Quiz.
Bruh.
Bagi jawapan last, sir.
Bruh.
Jawapan last.
Quiz submit on Thursday.
Oh my god.
Okay.
Sir,
Hmm.
Sir,
orang
sir,
tak
minggu ni compact je. Minggu ni
Apa?
compact.
Minggu ni complete.
Banyak sangat minggu ni.
Kejap je. Saya bagi exercise 1 as the quiz. The simplest
Satu
one.
je.
Satu je, sir.
Okay, satu je, sir.
Wow.
Thank you,
Okay.
sir.
Direct, sir. Thank you, sir.
Exercise 1 as the quiz.
Thank you, sir.
So the way
Thank
you
you.
answer is just like this. You just mention the name. Basically, you just write. You just mention the name. For example, like this. OP1. What is the type of the amplifier? OP2, what is the type of amplifier? O3, OP3, what is the type amplifier? And
Alright,
calculate the V out. So basically that you have 4 answers. OP1, OP2, OP3, and V out. 4 answers.
alright, sir.
10 marks
Okay, sir.
for the quiz. This is quiz number 2, right?
Yes.
Yeah, quiz number 2, right?
Sama tu.
Okay.
Yeah, betul.
Exercise 1 je kan?
So
Yang lain tak payah
siapa exercise 1 ya?
So
As
exercise
the
1
quiz.
lah submit lah.
Huh?
Exercise 1 lah submit.
Yes, submit exercise 1 as
Okay
the
lah.
quiz.
Yes.
Exercise 2 we'll do on the what do you call it in the lecture on Thursday, because this one I think is a bit difficult for you. Actually it's easy.
This summing.
This is easy. This is actually different.
Dia gabungkan ni kan difference.
This is difference amplifier.
Amplifier.
Puyo.
Basically, this is the difference amplifier. Which the ratio is what?
Rasa. V1 dengan V2. Lepas tu baru kita guna difference.
V1 is the input, but this one, you see this example, it given the output, it given the one of the input, and find the another input instead of giving the 2 input and find the output. So you see, the question is a bit tricky. It gives the output and one of the input, and you need to find the another input V1 instead of given V1 and V2 and find V out. And another one is that find the value of the IL, the current.
So dia ada 3 lah. KCL dia ada 3 dah.
What 3?
Dia punya dot tu ada 3 lah kan sir?
Dekat 1, 2 dengan yang IL lah sir.
Mana dot
dekat
mana?
Tu. Dekat
Ni.
kan 1
Ni.
dengan hujung.
So it's a bit what I call it difficult for you, but it's actually not that difficult lah. Right?
Alright, sir.
Right,
So then this actually example the design using inverting circuit, design amplifier with a voltage gain of itu, then redesign your circuit using non-inverting circuits.
Design kita buat lah circuit tu sir.
Calculate the RF and R1.
Ya lukis lah. Kalau lukis ada markah.
Yeah, of course lah, kena lukis lah.
Alright sir.
Okay, so this is the exercise, right? So that is the end of the amplifier. So we have covered all the material that we need to cover for the digital, for the analog electronics. And next week we'll go into the digital electronics. And actually you are ready for the test 1. Test 1 will cover the analog circuits. So make sure that you start your revision on the analog electronics, so that we will have test 1 during this MCO, the PKP.
Test akan jadi online test macam ni sir?
Online test, or it can be take home test, it can be open book, open note test.
Sir,
Yes.
open note test.
Wih,
Ilmu belum ada.
ilmu belum tak
So-
kadang open book pun
So most probably that what I'll do is that you have 24 hours to complete the test. So it's open book, open note test. After 24 hours, you submit online and we grade.
Alright.
Okay.
Okay.
Alright.
So any question?
No, sir.
No.
When is it, sir?
Huh?
Applications.
What application? Basically
yang
that there will be two questions for the test one. First question will cover on the semiconductor, on the diode, and on the BJTs. And the second question is on the amplifier, OpAmp. Okay?
Alright, sir.
So there will be two questions for the test. So since it will be most probably is a open book, open notes, and then take home kind of test. So maybe you have to expect it will be a bit more difficult than the closed book, closed notes.
Alright, sir.
Like hibiscus circuit last time, sir. Like the flower circuit last time, sir.
Maybe, I don't know. Let's see how. Right?
Okay.
Okay. So my lecture is actually 2.5 hours. It's more than 2 hours.
Yes, sir.
Wow. Okay. So you have other lecture after this?
Yes, sir.
What time?
2:30, sir.
2:30. Okay. So
2:30, sir.
basically, any question?
No, sir.
No question. Then basically that I can stop the recording, and if you have any question, you can ask me later or in the WhatsApp. You can WhatsApp me anytime. Okay.
Give me a
Thank
WhatsApp.
you. WhatsApp lah. WhatsApp boleh, email boleh. So I'm actually reachable by both WhatsApp and also email. Okay. So thank
Okay.
you. See you on Thursday.
Thank you, sir.
Okay, sir.
Okay.